Hello, today we're going to be looking at taking the derivatives, antiderivatives of functions where the base is not e. And this is very easy for us to do. The first one we're going to look at is a to the u. To do this, we're going to derive the formula. And we have y equals a to the u. I'm going to let y equal a to the x just to make it a little bit easier. Now, we're going to use logarithms to solve this. Matter of fact, it's called logarithmic. Differentiation. And if you watch one of my earlier videos, we kind of showed this a little bit. Basically, what logarithms can allow us to do is to bring down powers. So I can't take the derivative as is because I have a power in a variable in the power there. So by taking the natural log of both sides, I'm allowed to bring down the power. Now, why natural log and not base a? Well, I know natural log's derivative. Then we get the natural log of y equals x times the natural log of a. The derivative here, you have to use implicit. So 1 over y times dy dx equals, over here we have a product rule, the first times the derivative of the second. Remember, natural log of a is a constant, so I can just write that as 0. Plus the second, the natural log of a, times the derivative of the first, which is just 1. So when I simplify this, we're going to get 1 over y dy dx equals the natural log of a. Solving, therefore dy dx becomes y times the natural log of a. I can now replace the y. We know what y is from the beginning. So therefore, our derivative in the end becomes a to the x natural log of a. Very easy to do. So we're going to get a to the u over here because we're using u, a natural log of a. Now, we use u because there's like a substitution in here. We take the derivative of u, du dx. That's just our chain rule, which we'll talk about in a few moments. Taking the antiderivative, very easy. We just do the opposite. Remember, the antiderivative is just the opposite of a derivative. So I'm going to get a to the u back, but instead of multiplying by the natural log of a, this time we divide by the natural log of a, plus your c1. So we get a to the u divided by the natural log of a plus c1. There's our rule for antiderivatives there. Now, the last rule that we're going to learn today is the log base a of u. Be careful, don't confuse this with natural log. Now, natural log is very easy. This one's a little bit more complicated. So I'm going to start off by writing it as the log base a of u. And make it simpler though, let's change that to an x. I am going to rewrite this as an exponent. So by writing it as an exponent, it's going to allow me to use logarithmic differentiation. So to write this as an exponent, I use something called logarithmic differentiation. Exponentiation. Sorry, not logarithmic, it's just exponentiation. I exponentiate both sides, and I'm left with a to the y equals, I exponent by a, the base, because that's going to cancel those out. And I'm just left with a to the y equals x. And you know how to write those, though. That's just another way. Taking the natural log of both sides now is going to allow me to bring the power down. Now if you notice, I'm using that logarithmic differentiation. Product rule, the first times the derivative of the second, remember that's just 0, plus the second times the derivative of the first. Well, what's the derivative of y? Just dy dx. And that equals 1 over x. Goes away, so we get dy dx equals 1 over x times the natural log of a, if I divide. And there's our derivative. Now it is almost like natural log. It's 1 over whatever that is, but we got to multiply by the base on the bottom. So in generic terms, we're going to get 1 over u times the natural log of a times du dx. And again, the du dx, that's just our chain rule right there, which we'll see in just a few moments, like I said. Alright, so let's practice some derivatives here. Very easy to do. I have y equals 2x cubed. So this is my exponential. My rule says, here it is. It says, just to write this as 2 to the x cubed times the natural log of the base, which is 2, times, don't forget your chain rule here, 3x squared. And there's your answer, and we just leave it alone. With antiderivatives, with logs, the same thing. There's my rule. I have the log base 3 of x squared plus 1. So my rule says to write it as 1 over x squared plus 1 times the natural log of the base. Remember where that natural log came from? It came from when we did the implicit differentiation. And we multiply this by 2x, your chain rule. So you can rewrite this as 2x over x squared plus 1 natural log of 3. And there's your derivative. Very easy to do. Now let's take a look at a slightly harder one. Now if you notice here, we have y equals x plus 1 to the x minus 3. This is a variable to a variable. This is a lot harder than it looks. It's not a power rule. It's not a chain rule. It's not a product rule. It's not a quotient rule. So this is a weird one. So what we have to do is we have to bring the power down. If I bring the power down, if I can somehow multiply this power by this, I can make this as a product rule. So I think, what allows me to bring down powers? Logarithms. So I am going to use logarithmic differentiation. Very easy to do. So my rule says to take the natural log of both sides. And by doing so, I'm allowed to bring down the power. So when I do the natural log of y, we get 1 over y, dy dx. Over here, product rule, the first times the derivative of the second, 1 over x plus 1, plus the second times the derivative of the first, which just becomes 1. Multiply both sides by y, I ran out of room, so dy dx, we get quantity x minus 3 over x plus 1 plus the natural log of x plus 1, and I multiply all of that by y. Very ugly, yep. But I'm still not done. I'm going to replace the y. So we would get dy dx equals x minus 3 over x plus 1 plus the natural log of x plus 1 times y, sorry, parentheses there, times y, which we know what y is, that's the original function, x plus 1 to the x minus 3. And there's our final answer. Isn't that lovely? Alright, so let's practice some antiderivatives. Very easy. 2 to the x. Our rule says it's exponential. Have you noticed anytime we take a derivative or an antiderivative with anything exponential, we always get that exponent back? We're going to divide here though by the natural log of 2. Remember yesterday with natural log, with e to the x, we would get e to the x over natural log of e. We just cancel that e out because it's just natural log of e is just 1. But here, not going to cancel, we keep it. So plus c1. Don't forget your constant. Alright. The next one, x cubed. This is our use substitution, so we can use a shortcut, x cubed. du is 3x squared. dx equals du over 3x squared. Kind of the shortcut, I know the x squareds here will cancel. And I write out what's left. I'm going to have 3 to the u, but I'm still having this 1/3 on the outside. Don't forget about that. du. Taking the antiderivative, we get 1/3 times, this becomes 3 to the u plus c1. Or 1/3 times 3 to the x cubed plus c1. Now there's your answer. We can write this, I forgot over the natural log of 3, over the natural log of 3, over the natural log of 3. I always forget that. Be very careful, very easy to forget. So I can leave this as my answer, or I can write this as various other ways. Of course, there's obviously the simple way, over 3 natural log of 3 plus c1. But if I use my log properties, give me a second here. Yeah, timed out. If I use my log properties here, if we use the log properties, hold on here, having trouble, technical difficulties. Come on. there we go. Sorry about that. If we use our log properties, we can write this as 3 cubed. So I can go 3 to the x cubed over natural log of 27 plus c1. And lastly, if I want to be real fancy, these have the same base. I can subtract the powers. I can write this as 3 to the x cubed minus 1 over natural log of 3 plus c1. All various ways we can do this. The more you know about logarithms, the more you can actually kind of simplify things. And this is pretty easy. We'll talk about this next few days. So take a look there. Hope you guys had fun. I enjoyed this video. Hope you guys enjoyed this much too. Bye-bye.